By the end of this lesson, you will understand how people represent the shape of our world and divide a surface into useful parts. Imagine walking into a classroom where a round Earth model stands beside a flat world poster. On the same table lie a cinema ticket and a chessboard. The objects seem unrelated, yet each one offers a clue about representing a large surface and finding a particular place on it. A globe is a spherical model of the Earth, so it keeps the Earth's basic shape and relative sizes more accurately. Flattening the curved Earth into a world map always stretches or changes some areas. The opening surface reveals the key comparison. A globe matches Earth's spherical shape. That shared shape reduces the distortion caused by flattening the whole world. A curved surface cannot become one flat rectangle without stretching, tearing, overlapping, or wrinkling, like a fruit peel. A globe avoids this flattening problem, which makes it useful for representing the whole Earth. The fruit peel idea makes the limitation easier to see. Flattening a sphere changes its surface. Some shape, size, or spacing must be altered on a flat world map. Compare the curved and flattened surfaces. Why does a globe represent the whole Earth more accurately than a flat world map? The shape of the model gives the reason. A globe shares Earth's spherical shape, while flattening the whole world distorts something. The stretched edge areas show that change. Next, we will examine the globe's axis and the north and south poles. The axis is an imaginary line through the Earth's center, with the North Pole and South Pole at its ends. A classroom globe may have a supporting needle, but no real rod passes through Earth. The solid and dashed lines must not be confused. Earth's axis is an imaginary line. A classroom globe uses a physical needle only to show that idea. The globe stand makes the axis easy to see, but the axis is an idea rather than a physical object. It gives us two opposite endpoints that can be named consistently as the North and South poles. The model adds hardware that the real planet does not have. The poles are endpoints of the axis. They are locations defined by the imaginary line. Compare the solid needle with the dashed line. What are the axis, North Pole and South Pole, and does Earth have a real needle? The two views separate the model from reality. The axis is an imaginary line. Its endpoints are the North Pole and South Pole, and Earth has no real needle. The solid needle belongs only to the classroom globe. Next, everyday seats and board squares will help us understand the idea of a grid. A grid uses two crossing clues to locate one exact place. In a cinema, row C and seat 7 meet at C7. On a chessboard, B and 4 meet at B4. The two highlighted bands make the common rule visible. A grid location needs two values. One clue identifies a line, the second selects one place on it. One row or one seat number still leaves several possibilities. Combining both clues leaves only their intersection, which is why a grid can identify one precise location. The remaining choices show why one clue is not enough. Two clues remove the ambiguity. Their intersection identifies one exact position. Use both everyday examples together. What is a grid, and why do C7 and B4 each need two pieces of information? The crossing highlights show the shared pattern. A grid uses crossing rows or positions, and two clues are needed to select one exact place. C7 and B4 each combine one clue from each direction. Next, we will test why one grid clue leaves several possible locations. One grid clue narrows the search, but two values identify the exact location. D alone gives a whole column and 6 gives a row. Together they meet at D6. The three boards show the search becoming more precise. One grid value leaves several choices. The second value selects the single intersection. The letter and number identify different crossing lines. Neither line alone is enough to choose a square. but requiring both conditions leaves one intersection and prevents a wrong location. The intersection is the only place satisfying both conditions. A complete grid address has two parts. Both parts must be read together and in the correct form. Compare how many squares remain in each view. Why does D6 identify one square while D alone or 6 alone does not? The intersection provides the complete explanation. D6 combines two crossing clues, while either clue alone leaves several possibilities. Only one square satisfies both values. Next, we will identify the equator and the two hemispheres on a globe. The equator is an imaginary circle halfway between the poles. It divides Earth into the northern hemisphere above it and the southern hemisphere below it. The equal halves reveal the circle's defining position. The equator lies halfway between the poles. It divides Earth into northern and southern hemispheres. The equator is a shared reference line, not a physical band around Earth. Because it is midway between the poles, it consistently divides the globe into northern and southern halves. The dashed line protects us from a common misunderstanding. The equator is imaginary, not physical. Its value comes from the shared way it divides the Earth. Use the poles, dashed circle, and shaded halves. What is the equator, and which hemispheres does it define? The middle circle and labels provide the complete response. The equator is an imaginary circle halfway between the poles, and it defines the northern and southern hemispheres. The dashed line shows that it is not physical. Next, we will preview how two sets of lines can build a grid on the Earth. An Earth grid also needs two sets of crossing lines, but they curve to follow the globe's surface. These line families are called latitudes and longitudes in later lessons. The bent grid preserves the rule learned from seats and squares. Earth's grid needs lines going two ways. The two future line families are called latitudes and longitudes. One set of lines would leave many possible places along each line, just as one cinema row leaves many seats. A second crossing set narrows the location, even though the lines bend on a sphere. The same two-clue logic survives the change in shape. A curved grid still needs two directions. One line family alone cannot identify one exact place. Follow the two line families from the flat grid to the globe. What two kinds of lines will future lessons use to build the Earth's grid, and why are both needed? The labels and crossing patterns supply the response. Future lessons use latitudes and longitudes, and both are needed because a grid requires two crossing clues. This lesson introduces only their names and shared purpose. Next, we will reconstruct the globe and grid ideas without adding any new information. A globe matches Earth's shape better than a flat map. Its imaginary axis ends at the poles, and the equator divides two hemispheres. Like C7 or B4, Earth's grid needs two crossing clues to locate places. The connectors show how the separate lessons fit together. Globe features and grid clues form one system. Each visible part supports a different kind of understanding. These ideas work together. The globe represents Earth, the axis and poles provide opposite reference points, and the equator gives a middle line. Grid examples show why two crossing directions are needed for exact location. The final image is useful because every conclusion points to evidence. Each Earth idea has a visible clue. The shape, lines, halves, and intersections can all be explained. Use the 4 clue clusters around the globe. How do the globe, axis and poles, equator and hemispheres, and grid rule connect? The completed reconstruction links all 4 parts. The globe models Earth's spherical shape. The imaginary axis ends at the poles. The equator divides the 2 hemispheres, and a grid needs 2 crossing clues. Each idea helps describe or organize the Earth. You are ready to use this foundation when the next lessons examine Earth's grid lines in greater detail.